Okay, so this is your unit 6 for simple strain, your module 2. Okay, so our unit 6 is thermal stress. Okay, this is now all about thermal stress. So if you say thermal stress, if you say thermal, that is literal by means or by because of temperature. We are talking about here temperature. Okay, so it is a stress due to temperature. So in this unit, we are going to solve problems regarding thermal stress and deformations. Okay. So if we say thermal stress, okay, if a temperature deforms, if temperature deformation is permitted to occur freely, no loads or stress will be induced in the structure. In some cases where temperature deformation is not permitted, an internal stress is created. The internal stress created is termed as the thermal stress. Okay, so let's try to put it this way. Let's say this is the member. Okay, this is the member. If that is just a free member, there is no support. Okay, that will restrict the this member. Then isn't it recalling your physics or your chemistry? A temperature will always affect a certain material. So if that temperature is high, there will be an expansion, isn't it, on the materials of this? Okay, on the material itself there will be an expansion that is very small, so that is not visible, of course. If the temperature will be freezing, okay, that will be a negative temperature, then that also affects by making your material shrink, okay, or contract. So that movement or that deformation, that is actually a deformation, isn't it? Expansion, okay, that can elongate or expand, and then contraction that can shorten, okay, or shrink. So that deformation will actually have no effect on, there is no, what do you call this one, stress. There will no be induced stress on the member if that member is free. Okay, if that member is free, then that is free to expand and then contract. There is nothing experienced by the member. But, okay, let's say this is restricted due to a support. Then if this will expand due to an addition on temperature or very hot temperature, that will expand. So the materials will exert an effort to itself because that is restricted. So that stress because of expansion, or the other way, if that will shrink, okay, and that is restricted, those deformation will create an stress, and that is what we call as thermal stress. Okay, so that is due to the member which is restricted. That is only true to a member which is restricted. If that is a free member, then there's no problem. There is no thermal stress created by elongation and shortening. But since that is restricted, there is a thermal stress. Okay, so that is what we call thermal stress. So temperature changes cause the body to expand or contract. Okay, so again, we compute that deformation. Let's try to put that sub T means deformation due to temperature. Okay, and that is equivalent to alpha L times TF minus TI. Or again, this is what do you call this one? You can change this one into delta T. What is the meaning of delta T? That is change in temperature. Okay, you discuss this one. I think the change in temperature. You discuss some of this, or maybe this formula in your physics. Okay. So delta there, I mean alpha there. I'm sorry, this is alpha. Okay, alpha there is your coefficient of thermal expansion. So as we know that different materials behave with respect to temperature. There are materials which easily expand, or which will easily expand or contract in just a small amount of change in temperature. There are also a material wherein that will have this just a small the thermal deformation within a given high temperature. So different types of material will behave in a different way, and that is contained by this alpha. Okay, that is actually this property alpha. It contains the behavior of the material based on the amount of heat, okay, received by that. So okay, that is in the unit meter. That is expansion in meter per meter degree Celsius. Okay, or actually this could be given on also as radian per degree Celsius. Okay, since meter cancels, or in English this could be the equivalent. So your L there is the length, and then TF is the final temperature, TI is your initial. Or simply, okay, if your TF and TI is not given, rather you are given the change directly, then you do not need to subtract this TF, TI. Okay, if you are given directly your change in temperature. But if you are not given that change in temperature, you are rather given the final and the initial, all you need to do is subtract to get your change in temperature. Okay? So again, that sub T means thermal deformation due to temperature. Okay, so thermal stress. So these are the general steps for us to follow. So a general procedure for computing the loads and stresses caused when temperature deformation is prevented and is outlined by these steps. So first is imagine the structure relieved of all the applied loads, constraints so that temperature deformation can occur freely, and then represent this deformation on a sketch and exaggerate their effect for us to see that one. Okay, so for us to evaluate the effect of thermal, let's focus on the thermal itself. Okay, let's forget about the other loadings. Let's forget about the support. Okay, so let's say this is your member. Let's forget about the other loadings. Let's just focus on the thermal effect of that. And then second is now imagine the sufficient load applied. So first, your step one is try to apply. Okay, let's say there is a drop. If we say drop, that there is a reduction. So if there is a reduction, that is a negative. Okay, the change. Look at this. If your final temperature is smaller compared to your initial, what happens? The temperature of the body reduces. So that will make this contract, okay, or that will shrink. So therefore, your delta T is a negative. This TF is smaller than that, so that is a negative number. Okay, your change in temperature is a negative. That will give us a negative deformation because, as I've said, isn't it? As we discussed on the previous unit, wherein the shortening, especially if we are combining deformations, like there is a shortening, there is an expansion, it is better for us to have a sign convention. Wherein a shortening, let's put that as negative. The elongation, let's put that as positive. Okay. So again, let's say for an example only, let's say that is a reduction of temperature, then this will shrink. So let's just try to exaggerate that one, but in actual that is just very, very small. Okay, let's just try to exaggerate for us to see. Or you can consider a expansion, or that will be extending this way. Okay. So now imagine the sufficient loads applied to the structure to restore it to the specified conditions of restraints. Represent this load and correspond load deformation on the sketch step 1 for step 1. So now let's try. Okay, we can solve that one. Yes, we can solve. But for us to know the stress, okay, we need to have an equivalent force. That is the question there. Yes, you can solve directly your deformation by merely using your formula alpha L delta T. Once you have your change in temperature, you know the length of that. This will always be given, okay, in a certain type of material that will be given, okay. These are actually, how did we end up with this? These are given on a specific type of material based on experiments, okay. So if they have this new type of material, they will try to do experiment on that. What is the reaction of this in thermal? What is the reaction of this in different loadings? So this type of material, they will have a specific thermal coefficient, this alpha. This is why we call this one coefficients. We have also this property like E. We have that also like J. So these values of the certain material, that is defined by means of experiment. Okay. So we will not question about these coefficients. So we are going just to use these ones. Okay. So again, as I've said, once you know this, given this coefficient, the length and the change in temperature, you can solve actually directly your deformation. So this is reversal. Okay, we can solve directly your deformation without knowing the force experienced or being held by that material. So now we know the deformation, but this time we need to know the stress, and for us to have a stress, we need to have a force, isn't it? So let's try. Okay, so actually the force being exerted on the body itself due to thermal, let's try to put there a dummy P, okay, a dummy load P. just to represent the force being exerted on the material due to temperature. So let's just put there a force P. Okay, but that is actually not there. Okay, that will just represent the stress because of the temperature. And then if we know that P, then using the cross section we can have the thermal stress that we are referring to. Okay, so the geometric reaction or relation between, so what will I do? Okay, for me to return this one to its original state, I will try to direct that one the other way. Okay, so that is our P, but that is actually a compression. Okay, since that is actually shrinking, then that will be a compression. If that is expansion, then that is a tension. Okay, so this is just a reaction. But the actual stress is, if that is shrinking, that is compression. If that is expanding, that is tension. Okay, so it depends. It depends. I'm sorry. Actually, the other way. If that is expansion, due to your supports here, due to your restriction, that will be compressed. So that is a compressive stress. I'm sorry about that. Okay, please do not be confused with that. If this is if this will shrink, okay, it means that that is attached here. So that will resist this from shrinking, but there will be a stress that will be developed. So that is a tensile. Okay, so you need to differentiate these two. If your material, if your member will expand, but there is a restriction, okay, there is a restraint, then that will undergo compressive stress, which is due to temperature. But if that material will try to shorten, and that is still attached on the both ends, that will undergo tension. Okay, tensile stress or tension. Okay. So the geometric relation between the temperature and load deformation on the sketch given the equation. Okay, give the equation that together with the equations of your equilibrium may be solved for all unknown quantities. Okay, so together with your equilibrium equations, again using this equation that we will establish in your thermal stress, we will solve for the unknowns, okay, on the problem. So let's try to have an example for that. Okay, so we have here a steel rod 2.5 meter long is secured between two walls. Okay, so it means that it's restrained. Therefore, if there's a change in temperature, then there will be a stress since that is restricted. Okay, because of this wall, two walls. So let's say these are the two walls. This is the rod, steel rod, 2.5 meter long. Okay, if the load in the rod is zero if the load in the rod is zero, or it means that is the stress on the rod is zero at 20 degrees Celsius, then compute the stress when the temperature drops to negative 20 degrees Celsius. So that is your initial temperature, but if that will become a negative, it means that will be freezing, then there will be a shortening, isn't it? Originally that is 20 degrees Celsius, and that will become a negative 20 degrees Celsius, so that will be freezing, so that will shrink. Okay, the reduction of the temperature will cause the material to shrink or to contract. So that's it. But this is actually restricted, so this is just to exaggerate, but actually that is still, even if that will contract, that is still connected to the wall. Okay, so let's just exaggerate that for us to see. Okay, and then that will be brought back by the dummy force P, so that is still connected, since again, as I've said, that is restricted. Okay, secured between two walls, that is connected to your walls. So therefore, there will be a, okay, what will happen, this is contraction, so that there will be a tensile stress. Okay, tensile stress po yan. So length is 2, you can write this down, okay, given 2.5 meter length, okay, your initial is 20 degrees Celsius, your final is a negative, okay, your area is, you are given here your area 1200 millimeter squared, and then your alpha, that is your coefficient, okay, 11.7. Your mu there means micro is times 10 raised to negative 6, okay, so that is the equivalent of that. You need to put that so that your meter and meter cancels. Okay, and then your E, I want to put that in megapascal since I am using your Newton and millimeter, so I want to put that in megapascal. So gigapascal multiplied times 10 raised to 3 will be megapascal. Okay, so Look at this. The what do you call this one? The deformation due to temperature, okay, due to temperature is this one, but that will be brought back, okay, that will be cancelled due to the stress that is being experienced. And that is true because again, there will be a stress that will return that back because that supposedly is to be still attached, okay, that is restricted. So whatever is experienced, that will always be restricted. So there will be actually no change in length. That is just to for us to symbolize the effect of the temperature. Okay, but actually this will not happen. It will not leave a blank, or it will not leave the wall. So again, for us to return that one, okay, I will have apply there a dummy force P. Okay, so the effect of that is that deformation due to temperature and the deformation due to the stress, okay, if I will submit that one, that should be 0, which is actually our case. There should be no indentation since that will be restricted. Okay, so if I will submit that one, that should be 0. So rearranging, this will go negative on the other side, and then changing your this one, this one without subscript is just the normal stress, isn't it? So playa. But again, we do not have P since that P is actually just a dummy. What we know is what we are trying to figure out is a stress. So you can change that P over A as a normal stress. Okay, you can change that one. So that is sigma L over E. So that will be our delta here. On the other side, your deformation due to temperature, going back to our formula that we discussed, delta, or I mean alpha L delta T. See. By the way, you might be confused. This is a big delta, that is small delta. Okay, big letter delta, small letter delta. So that's it. Your small delta T, which is a negative here, we will change that one by its equivalent due to temperature, isn't it? So alpha L delta T, but negative. Okay. So rearranging, since actually what we have, we can solve directly this given the properties and the temperature. We can solve that one directly. So what we are trying to find is the stress, because that is the unknown here, isn't it? Compute the stress. Okay, that is the unknown here. So this is the unknown, sigma. So cross multiply on the other side. So you will have this. Sorry. Let's just change that one. Why is it? Okay. Why is it that there is no L already? Because your L and L cancels. If I will cross multiply that down, that will cancel. So leaving us our E, cross multiply it here will be a product. Okay, so we are good. We have that alpha, we have that E, alpha E, we have that change in T by subtracting, then we can solve that stress. Okay, so substitute your TF. Okay, TF is negative 20, substitute together with the sign, of course, for us to follow the rule of algebra. Minus 20, a positive, so we will end up with a change in temperature as negative 40 degrees Celsius. Okay, so I will input that as in negative. Okay, so that negative in negative will make it a positive. It is now a positive stress. So what is a positive stress again? That is compression, isn't it? Okay, compression. A negative stress is a tensile stress. Okay, so that's it. Substitute. All I need to do is substitute your alpha. Okay, your negative is just the negative there. Okay, your alpha is as in just copy that one times 10 raised to negative 6 because of that micro. And then your L, your length, first that I do not need to substitute that, so actually that is needed. And then what else do we need is your E. Your E times 10 raised to 3 to make it megapascal. And then your delta T, which is negative 40 degrees Celsius. So look at this. Degrees Celsius below cancels with that. This is all over. That means all over, so that will be below. Cancels. Meter cancels. So we are left with megapascal. So calculating will be giving us 93.6 megapascal. Okay, so that is for number 1. Let's have one more. Okay, one more. So almost the same, but this time, okay, almost the same. The givens are the same. The area, the final, and the initial, and the length are the same. Your E and then the coefficient of expansion is the same. The only difference here is that we will now be considering that the wall, okay, will also follow. Okay, the other wall will follow. So long is secured between two walls. If the load on the rod is 0 at 20 degrees Celsius, compute the stress when the temperature drops to negative 20 degrees Celsius. The area is that, and then given these values, assuming that the wall, okay, so this is the difference. Assuming that the walls spring together a total distance of 0.5 millimeter. So it means this member will not leave. This will not leave your wall. Okay, but the wall will move. Okay, so that is the meaning of that. The wall, together with that end of the member, will move a 0.5 millimeter due to temperature. So it means that temperature will affect the member, and at the same time, the wall will be affected by the temperature. But that is still restricted. Okay, so it is still connected. So what does that mean? So look at this. If this will move, okay, your member, let's say that will shorten because that will drop to negative. So the same scenario as our first example. That will have a deformation, okay, which will be a shortening. So delta t, delta sub t. And at the same time, the wall will undergo a deformation, which is 0.5. Okay, that is the same direction going that way. Okay, it will follow that way. And then your unknown P or your dummy P will try to return that one. So you will have this to be returned, for this member to be returned to the wall, you will have that stress, okay, experienced by the member. And at the same time, that P will totally close, okay, all in all of that. So what will just be the change here is that instead of having that equivalent, wherein your stress is equal to your negative stress due to, your deformation is equal to negative deformation of temperature, what we will be having here is additional that one, addition of that 0.5, okay? So your temperature is equivalent to negative, okay, look at this, your temperature is a negative of the summation of that. Look at this final figure here. Your deformation due to temperature is a summation of the stress due to the stress, and then the given movement of the wall, which is 0.5. Okay, so if I will add this one, that should be equal to your temperature, but for that to be returned, that should be a negative. One of these should be negative. So that I will transfer this will be equal to 0. It means these are still in equilibrium. So that's it. So rearranging, since what we are trying to find is the stress, so that is found here, not there, since that is solved directly by the formula, and that is just a number. So rearranging, this will be a negative, and then this will transfer as a positive on the other side, or this will be left negative here, but the negative 5 will go positive, so it will be added here. Okay, so change again your stress into PLAE, but your P and A, since actually we do not know that P, that is just a dummy, so we can change that P over A as the stress, so stress L over E. So this is a negative, so put that as a negative. And then again, your deformation due to temperature is alpha L delta T plus that 0.5, okay, then rearranging so that you will figure out your sigma, okay. But first, we need to find your delta T, but which is actually the same as a while ago. So cross multiply this one. So together with that L, it will go negative, carry the negative so that you will have the stress. So enclose that one since this is totally multiplied to your value from the other side. So that's it. So all we need to do is substitute. Your E is that. Okay, your E is this. Your length, I want to put this, again, since I am using a megapascal, which is Newton per millimeter squared, I'd rather transform all of that into Newton and millimeter. So your length will be in millimeter. Okay, your 2.5 will become 2,500. This, no problem with this. You do not need to transfer that in millimeter, since this will actually cancel out. Okay, so there's no problem. All I need to do is copy. And then your delta T is a negative 40, which cancels that degree Celsius. So substitute the negative, of course, so that will make it positive together with that. And then plus 0.5 will give us 53.6 megapascal. So what does that mean? Okay, look at this. In your first example, due to that reduction, due to that shrinkage of the member, okay, of our steel member, your member will undergo a compressive stress of 93.6 megapascal. In your number 2, since the wall is also affected by the reduction of the temperature, then that will also adjust, that will actually reduce because of that movement that way. Instead of having that 93.6 megapascal as a stress on your member, because your wall will undergo deformation so that it will actually help, okay, that member, then that will deform 0.5, then the stress will be reduced to 53.6. The compressive stress due to that reduction of temperature will be reduced from 93.6 to 53.6 megapascal. Okay, so that's it. That is for thermal stress. Again, what is thermal stress? Thermal stress is due to thermal deformations. It's either expansion or contraction, or what we call a shrinkage. So actually, what we have in our example is just contraction or shrinkage. If that is an expansion, your type of stress is different. That is a tensile stress. Okay, you will end up here, following the sign convention, you will end up with a negative, but the negative means compression. I mean not tensile stress. Okay, so this is what we discussed. This is what we followed, these steps. So these are the important concepts that you need to know. And this is the additional, wherein it says there that thermal stress is developed when normal internal force from the body is trying to resist thermal deformation due to change in temperature. Again, you will end up with an internal force because your member is being restricted. Means that is being connected to a certain fixed member. Okay, so that you will undergo a thermal stress. But if your member is free to expand or contract, then there will be no thermal stress. Okay, so that is for our unit 6, thermal stress, still on your simple strain, or we are talking about deformations here. So if you have any question, you can comment below the video, or we will discuss that on the live meeting. So thank you very much for watching. Okay, thank you very much for watching.